Thanks a lot. This is really fun for me. In case there's some of you who don't know who I am, since I haven't been around, I'm Steve Schall. I was at KU from 1972 until full retirement in 2009, and I now live in Tucson. It struck me a while ago that since your meetings are Zoom, that would be a great opportunity to have some talks by some of our KU alums, especially some who from the 70s who were rather strongly involved in the formation of AAL. And so one being Dave Tholen, who was just talking, one being Laurie Allen, who on my screen is right below him, and Umberto Campins is here also. So they'll be giving talks later on. And
by the way, that was my father. That wasn't me. I wasn't even born in the 70s.
Good luck with that one. And also, I see Stan Howerton is here, who wasn't an astronomy major, but was taking classes. And or Stan, were you a major? I guess you were. But
unfortunately, Stan does not have a camera nor a microphone.
Yeah. Oh, okay. So anyway, so what I wanted to share is, are you able to see the picture here?
Beautiful.
Yes.
We see it. Yes, looks great.
On the roof of Lindley Hall, there's Dave. This was during the very first astronomy camp that we had. And what they are doing is carrying the 27-inch telescope mirror to be reinstalled. We had shipped it off to be cleaned and re-illuminized. And so it came back. And so it took all these strong young men to carry this thing back to install it. So I just thought that, anyway, since that telescope doesn't exist at KU anymore, that's something that you don't see. I know the Clark refractor is still there, although not being able to be used now. I gather the dome's in bad shape. Since there was a time when the dome that was there before the current dome was in bad shape, that Laurie Allen one summer and a friend climbed up on there and repaired it. Remember that, Laurie?
As I recollect, we redistributed some construction materials found on campus.
Yeah, yeah, all without previous permission, as I remember. It appeared one day. So anyway, so Dave, if I have it right, was there from 74 to 78, graduating in 78, right, Dave?
Because, 78, class of 78.
Yeah, and then went to the University of Arizona, and that was cool because I was taking a sabbatical that year. So Dave's first semester at in planetary sciences at the U of A was during my sabbatical, and my office was also in that building. And so we saw each other quite a bit at that time. And Umberto then also went there, having spent a year at Rice University, and then left that to go to U of A. And so anyway, when they give their talks, I'll talk more about Umberto and Laurie when that time comes. So just don't bail out on us, guys, because you know I'm going to introduce you. So anyway, Dave at that time then really got into asteroids and was working with Tom Garrels and Ben Zellner. Tom Garrels was on my PhD dissertation committee and really important in my life. And I had an office with Ben and knew him. So it was really quite neat to be able to go from KU to then U of A and have these guys come down there also. And have really strong impacts in terms of the work that they did for their dissertations, and a lot then going on from there. So it's a great pleasure to introduce Dave Tholen.
Thanks, Steve. Before I get to the presentation, I was just thinking, you know, all the way back to college days. Do you remember our first encounter?
Embarrassing.
It's probably easier for me to remember than for you because, you know.
Okay, tell me about it.
Friday night open house, roof of Lindley Hall, lots of public around, 8-inch Celestron on that pier, and you were trying to find the Andromeda Galaxy, and we're having some difficulty.
Okay.
And
Naked eye?
no, with the telescope.
Oh, okay. Okay.
Yeah, I mean, light polluted skies and all that. You can't spot it naked eye. You have to sort of know where to look in Andromeda. But I came up and said, I think I can find it, and I did. So.
Well, that's probably not the first time you saved my butt from anything.
Anyway, okay, let me go into screen sharing mode here. And
I can find that.
okay, does everyone see the Big Dipper?
Yes.
Yep.
All right, so you're probably wondering, why the heck am I showing a picture of the Big Dipper? Well, on April 13th of 2029, that's a little over 8 years from now. By the way, that's a Friday the 13th. And an asteroid will come closer to the Earth than our geostationary communication satellites. And for a few hours, it will be as bright as a 3rd magnitude star, meaning it will be bright enough to be seen with the naked eye. And a 3rd magnitude star is the star here that connects the handle of the Big Dipper to the bowl of the Big Dipper. That is a 3rd magnitude star. So presumably you've all seen the Big Dipper on many occasions and have a pretty good idea how bright that connecting star is there. And that's how bright this asteroid is going to get on April 13th, 2029. And that's what this presentation is all about, the discovery of that asteroid. So with that being the teaser, we can cue up the theme music and run the opening credits. Ta-da! Okay, I need to get some theme music to go with this. All right.
You're not going to play the clarinet for us.
I was thinking of playing a recording of I'm a Jayhawk, or maybe the theme music from Stargate or something like that. But anyway, I had a difficult time trying to decide just how far back to go when talking about, you know, what really caused the discovery of this particular asteroid. On the one hand, you could go back, you know, 50,000 years to the event that created Meteor Crater near Winslow, Arizona. Hope many of you have had an opportunity to visit that impact crater. But you know, a lot of people will look at that and say, you know, that was 50,000 years ago. Things like that don't happen nowadays. But then you could look back at 1908, June 30th. We had an object collide with the Earth in Siberia near Tunguska, the so-called Tunguska event. About the same size object as the one that struck Arizona, but different composition. Arizona got hit by an iron object, whereas the one that hit Siberia was probably more carbonaceous, and it never actually made it all the way to the ground intact. It was an atmospheric explosion. It was just too fluffy to survive all the aerodynamic stresses upon entry. and it exploded probably about 8 kilometers above the ground. But the shock wave flattened the force, and I'm sure you've seen the pictures of the Tunguska event. And even more recently than that, we've had research done by people like Alvarez and others looking at the iridium layer and the connection between that and the Chicxulub impact event off the tip of the Yucatan Peninsula. That was 68 million years ago. And of course, that coincided with the demise of the dinosaurs. So there's been work done on Earth impacts off and on for a very, very long time. But I think the singular event that set the wheels in motion for the discovery of Apothis was the asteroid 1989 FC, which on March 22nd of 1989 passed about 420,000 miles from the Earth, just beyond the orbit of the moon. But, about 250 meters in size is the estimate for that object. That's not large enough to cause a global catastrophe. The threshold for a global catastrophe is probably 1 to 2 kilometers, based on work that Dave Morris and Clark Chapman have done. They have a book out, Cosmic Catastrophes, that some of you might have read. So probably not large enough to cause a global catastrophe, but large enough to produce regional damage. And it made headlines. And here's the kicker. We didn't see it coming. This one approached from the direction of the sun. And we didn't see it until it had passed the Earth, and it was March 31st. So more than a week after the close approach to the Earth is when it was finally seen. Most of you are probably familiar with the Chelyabinsk event back in 2013. That's another one that came out of the direction of the sun. We did not see that one coming. But this caught the attention.
But that one, by the way, Dave, sorry to interrupt, but that one caused the most number of injuries to humans of any meteorite.
Yes, mainly shattered glass because of the acoustic shock wave, you know, the sonic boom. It shattered glass throughout the city of Chelyabinsk. And I've heard estimates of about 1,600 people being injured by flying glass. And not just flying glass, I've seen videos of, corrugated metal sheds, walls being blown down and on top of people. So, yeah, lots of injuries from the Chelyabinsk event. Anyway, the reason I wanted the timeline to start with 1989 is because not only did this one make headlines, it caught the attention of Congress. And Congress went to NASA and said, what are you guys doing about this? And the response from NASA was basically, well, the probability of such a collision with the Earth is so low that we don't think we need to do anything about it. And I guess that kind of satisfied Congress for the moment. And then 2 years later, we had 1991 BA. This one came even closer than the moon, only 100,000 miles away on January 18th. This one was tiny. If this thing had hit, most of it would have burned up in the atmosphere. We might have gotten a few meteorite fragments on the ground, but not much in the way of damage. So really wasn't a big threat to the Earth, but it once again made headlines. And once again, Congress went to NASA and said, what are you guys doing about this? And NASA said, well, we're not really doing anything about it because the risk is so low. That was not satisfactory response to Congress this time. So Congress passed some legislation directing NASA to set up 2 committees. One more bullet there on 1991 BA. We saw that one just a few hours before close approach. So small, so it wasn't all that bright. And we last saw it about 5 hours later. That wasn't seen for very long. Very small object, very faint. Okay, so back to those 2 committees. Congress directed NASA to set up 2 committees. One was charged with how do we find these things before they hit? And the other was charged with, if we found one that was on a collision course, what do we do about it? And those became sort of informally known as the detection and the deflection committees. The detection committee was chaired by Dave Morrison, who happened to be a faculty member here at the University of Hawaii at the time. And he asked me to serve on this committee because I had been working on near-Earth asteroids and knew something about asteroid composition. My whole thesis was on asteroid taxonomy. So I had some expertise that he felt would be a valuable contribution to this committee. And we met 3 times in 1991, and a report titled The Space Guard Survey was submitted to NASA on January 1992. Now, the deflection committee was chaired by John Rather, and most people on this committee were basically nuclear weapons specialists, which is why they met at Los Alamos. And but they needed some advice from some asteroid experts as to compositions and structure, internal structure of asteroids. So there were a half a dozen asteroid people who were asked to serve on this committee as well, and I was one of them too. There was one meeting at Los Alamos, and there was a report written, and I never really got a copy of that report. I don't know the exact date that it was submitted. It was significantly behind the detection committee's report, about a year. So I put a question mark on that date, 1993. And then in 1993, what happened? Well, Gene Shoemaker and his wife Carolyn, along with amateur David Levy, were working at Palomar and discovered a comet that became known as Shoemaker-Levy 9. And you remember this one. It was tidally disrupted by a close approach to Jupiter in 1992. And orbit calculations showed that it would collide with Jupiter in 1994. There's a picture I'm sure many of you have seen, taken with the Hubble Space Telescope. A couple dozen fragments there of different sizes. And you've probably seen plenty of pictures as to the kind of effect it had on Jupiter. Now, not having a solid surface like the Earth, you might think that an object would just plunge into the atmosphere and never be seen again. But as you can see, there are some dark blemishes that resulted from those impacts. And, Jupiter being 10 times larger than the Earth, some of those blemishes are a good fraction of the size of the Earth. Just an infrared picture showing that these events produced a significant amount of thermal emission as well. The bright dot to the upper left is one of the Galilean satellites. So that band of bright dots near the south pole of Jupiter are all those impact events from comet Shoemaker-Levy 9. I mean, they all hit at different times because they were strung out by the tidal disruption in 1992. Okay, so having witnessed an actual event, a collision event between a small object and a planet in the solar system, basically what happened with these detection and deflection committee reports is that they were sent to NASA, and NASA forwarded them to Congress, and they pretty much went on the shelf, and not much happened as a result. So, well, they got their report. That's what they asked for. That's what they got, and not much happened. But after Shoemaker-Levy 9 hit Jupiter, Congress basically said, hey, we need to get serious about this. So they set up yet another committee. This one was chaired by Gene Shoemaker, and it met in 1995, and they finally got serious about the impact hazard. And Congress directed NASA to start funding some sky surveys to find near-Earth asteroids. Okay, now, here's one of the problems I had with the Space Guard Survey report. There was a figure in that document it's a contour plot. It basically shows where the best place in the sky is to look for near-Earth asteroids. And these contours were all centered on the opposition point. And during one of the committee meetings that was reviewing a draft of the report, I'm asking the question, well, how was this contour plot arrived at? And they said, well, it's based on some models that have been generated of the near-Earth asteroid population. And I said, well, how were these models derived? And they said, well, the models were derived from the known population. And I'm going, but the known population was found in opposition searches. So isn't this just a case of circular reasoning? You're just saying that the best place to look for asteroids is the place where we've been looking for them? And that's kind of like the old story about, somebody spilling a bag of quarters on the street at night. And the easiest place to find those quarters is underneath the street light. And so everybody goes to the street light to pick up quarters, and they have no idea where the quarters are in places that are unilluminated. And I gave a little example. Now, if I was standing in front of a blackboard, I'd probably pull out chalk and draw a little diagram, but let's take the Carl Sagan approach here and do a blackboard of the imagination instead of a spaceship of the imagination. So imagine a blackboard. You got a big dot in the center representing the sun. Then you got a circle around it representing the Earth's orbit. And then you can draw a cone, a shaded in cone, extending outward from the location of the Earth toward the opposition region of the sky. And that's where the telescopes would look on one night. One night later, of course, the dot representing the Earth would move 1 degree around the circle. And then you shade in another cone extending outward towards the opposition point. And then the next day, you move another degree. Well, over the course of the year, you've shaded the entire solar system except for a hole interior to the Earth's orbit. You've not looked there at all. And so my big question was, what if there's an asteroid with an orbit that is interior to the Earth's orbit? Something like that could approach us from the daytime side and hit, and we'd never see it coming. And to support my argument, I generated a plot of the histogram of aphelion distances for the known near-Earth asteroids, and it was a pretty flat distribution down to 1 AU, and then it dropped to 0. Brick wall. And I'm going, this is observational bias. We're simply not looking in the right place to find these objects. So I started writing proposals, but in order to demonstrate the feasibility, if you want to find an object interior to the Earth's orbit, you have to look very low in the sky just after sunset, low in the sky in the west just after sunset, or very low in the sky in the east just before sunrise, in order to find such objects. And no one had really done that before, at least not extensively. I mean, Tom Garrels did a search for Earth Trojan asteroids with the Palomar Schmidt, but he found nothing. So, we had to demonstrate some feasibility here. So in 1997, I started working with our 2.24 meter telescope at the summit of Mauna Kea, looking at small solar elongations. And I had a graduate student at the time by the name of Rob Whiteley. I was actually off in Chile observing at Cerro Tololo on the night where he actually found 1997 QK1 at a very small solar elongation. And then in 1998, we discovered 1998 DB9 at a small solar elongation. These are both near-Earth asteroids. And in 1999, we found a big one. 1999 OW3, about a 5 kilometer sized object. And what was interesting about this object is that it turned out to have an orbital period of almost exactly 3 years. So each time it comes to, I don't want to say opposition, I want to say observability and apparition, you know, there would be one point where it's close to perihelion and bright. And then there'd be another point where it would be outbound and most of the way towards aphelion. This had a fairly large eccentricity to its orbit. And you know that objects slow down considerably as they approach aphelion. So if you draw an orbit diagram here, you can have one point that's near perihelion. You have another point which is receding from the sun and most of the way towards aphelion, and then a mirror image of that where it is on the other side of aphelion now back to approaching the sun. Both of those distant cases, the object is far away and faint and very difficult to detect. It's easiest to detect when it's close to the sun, when it's nice and bright, but it's always at small solar elongations when it's close to the sun. And so that's why opposition searches never found this object. It was just too faint when it was in the opposition region. So I pretty much demonstrated the feasibility of discovering near-Earth asteroids, even with a relatively small field of view. And started writing some proposals to NASA, trying to get some funding to continue this work. And, you know, it was kind of a long shot, not too efficient. You needed a big telescope to compensate for things like atmospheric extinction. The more air you're looking through, the less light you're getting. So atmospheric extinction was a problem. Usually the seeing isn't as good low in the sky as it is high in the sky. And there's also geometric effects. And, you know, for the same reason, a crescent moon isn't as bright as a full moon. That's the phase angle effect. So these objects we computed are on the average 5 times fainter than they would be if they were at or near the opposition point. So we figured we would need a telescope with 5 times the light gathering power in order to be competitive. Now, most of the near-Earth asteroid discoveries at the time were being made with 1 meter sized telescopes. There was the Spacewatch camera project on Kitt Peak, which used the old Stewart Observatory 36-inch or a 0.9 meter. And Eleanor Helene was using the 1 meter geodes telescope at the summit of Haleakala for a search. And that was a 1 meter telescope. The Linear project, the Lincoln Near-Earth Asteroid Research Project, or Linear for short, they were using basically another 1 meter geodes type telescope, but it was not an operational facility, but rather a test facility near White Sands, New Mexico. And they were just cleaning up, finding near-Earth asteroids. But they were all in the 1 meter telescope range. So I was saying, in order to compensate for phase angle losses, atmospheric extinction losses, and seeing losses, plus higher sky background as well, we would need to use roughly a 2.2 meter telescope that would have 5 times the light gathering power. And coincidentally, the university's telescope, the Summit Mauna Kea, is a 2.2 meter telescope. So I figured we had good justification for using such a large telescope. But as I said, you can only use an hour or two at the beginning of the night or the end of the night. So it's a very inefficient thing. There's always the problem with the moon being in that part of the sky, which increases the background even more. So anyway, my first couple of attempts at getting funding didn't succeed. But in 2002, Tom Morgan came up to me and said, "I've got some extra money. You still want to do this project?" And I kind of looked at him incredulously and said, "Are you kidding? Of course." So I finally got some funding in 2002. And we were in the process of upgrading our CCD camera. It had a couple of 2K by 4K. Actually, no, this was the 8K camera. It had 8 2K by 4K CCDs in it. So they're arranged in a 4x2 pattern, and they covered roughly 19 arc minutes in the focal plane of the telescope. Not a very big field of view. I mean, linear was looking at, a couple of square degrees, and here we were talking about looking at 19 arc minutes on a side. But there was a proposal which had been funded to upgrade our camera. They were going to replace the CCDs with newer, more efficient, higher quantum efficiency devices, and they were going to put a focal reducer in front of it and get our field of view up to 36 arc minutes, which I thought was going to really help us find near-Earth asteroids. So I get funding and I don't have a camera because it had been taken out of service for these upgrades I just told you about. 2003, a year later, the camera is still not back in service. 2004, the camera is still not back in service. One of the guys that was responsible for upgrading this camera had gotten involved in the Pan-STARRS project that I presume you've heard of. And he was spending all his time working on this gigapixel camera, and this 8K camera was no longer of interest to him. So this camera upgrade was just kind of languishing. And here I am in the third year of my funding, and we haven't really had an opportunity to use this camera that we had said we were going to use. So I started writing proposals for other telescopes, including Subaru, the Bach 90-inch on Kitt Peak, which had an instrument called 90 prime, which had 4 4K CCDs at the prime focus of the telescope, which covered a square degree of sky. And my old grad school apartment mate, Roy Tucker, was working at the Imaging Technology Laboratory at the University of Arizona at the time. And so I asked for his assistance with some of the observing on Kitt Peak. And in 2004, on June 17th, my postdoc, Fabrizio Bernardi, and I were at Mauna Kea using Subaru and the Suprime Cam instrument, and we discovered a candidate NEO in some of those images. Suprime Cam had a 34 by 27 arc minute field of view at the prime focus of this 8-meter telescope. But June 17th was the last night of that particular observing run. So in order to get follow-up observations of this candidate, we were going to use the Bach 90-inch on Kitt Peak on June 19th in order to get some follow-up observations. And while we were looking for this particular object discovered with Subaru, we found something moving. It was at the right place in the sky, moving with the right speed. And oh, I just discovered a typo. It says postdoc Fabrizio Bernardi. That's a typo. It's Fabrizio. No, the first R there should be stricken. Fabrizio. He's an Italian. And so Roy, Fabrizio, and I are at the telescope on this night. We're looking for this object. We got the computer monitor there. We're blinking the images we had just taken, and we're looking at the computer screen. And Roy points to something and says, "Is this your guy here?" And I'm going, "Probably not, because it should be toward the upper left of the field of view." But nevertheless, it was moving about, if I remember correctly, 110 arc seconds per hour. And for us, the threshold for being of interest was 90 arc seconds per hour. Pretty much anything in the main belt would be moving slower than 90 arc seconds per hour at that solar elongation. So anything faster than that, we felt would be an object of interest. So even though it seemed unlikely to be our Subaru object, we went ahead and marked it down for follow-up, which we got on June 20th. So we got our second night confirmation, and that showed that it was indeed an object of the near-Earth variety. and it got the designation 2004 MN4 from the Minor Planet Center. And then, okay, before we go into that, let's show you the discovery images there. This is actually a stack. We took exposures in triples. So this is a stack of all 3 exposures just to improve the signal to noise ratio. And, you know, I've shown this picture many, many times, and no one has ever really asked how we knew to track at those particular rates. Because most sky surveys, they just track sidereally. And if the object is moving fast enough, the object leaves a trail behind. But here we're tracking the telescope at the asteroid's rates. But we didn't know that this object, it hadn't been discovered yet. So somebody really ought to ask the question, how did you know to track the telescope at these particular rates? And the answer, well, I've probably given it away by now because I just told you in the previous slide that we were actually looking for the candidate near-Earth object that we found with Subaru 2 nights earlier. So we were tracking at the rates of the Subaru object, the object that we were expecting, you know, the rates that we were expecting it to have, the Subaru object. So we got lucky in the sense because that concentrated more light on fewer pixels, and it improved the detectability of this object. If we had been tracking sidereally, I doubt we would have found it even with the 90-inch telescope. So there's a little bit of serendipity there, a little bit of luck. Subaru had something to say about the discovery of Apothis. By the way, another interesting bit of trivia. Since we discovered this object with the 90-inch and it was very close to where this Subaru discovery was supposed to be, this actually is not the Subaru object. The Subaru object was recovered later on and was linked up with, what's the designation? 1983 VB3, I think it is, which is a Mars crossing asteroid. So that one turned out not to be a near-Earth object. But since we saw this object in our 90-inch images, the question arises, well, wouldn't it have been in your Subaru images? So we went back and checked. We missed by 20 arc seconds discovering this with Subaru. It was just outside the field of view. So there's a little historical anecdote for you there. Okay, so we got data on the 19th and the 20th of June, 2004. We had the night off on June 21st. Somebody else was scheduled to use the telescope. Same thing with June 22nd, another night off, telescope still being used by another observer. We were back on the telescope June 23rd. It rained. Monsoon season in Arizona doesn't usually start until Independence Day. This is June 23rd, so it's a couple of weeks early for it to rain. We had one night left in our assigned time, June 24th. It rained again. By that time, the crescent moon had moved into the part of the sky. The solar elongation was actually decreasing. This was an evening object. It was only moving 110 arc seconds per hour, whereas the sun is moving 150 arc seconds per hour. So the solar elongation is decreasing. It's just getting lower and lower in the sky. And now the moon's in the way. So by the time the moon's out of the way, it's pretty much impossible to recover this object. So we only got 2 nights on it. And then on December 19th, 2004, Gordon Garrett found a near-Earth object candidate from Siding Spring Observatory in Australia. And the Minor Planet Center quickly identified it as being the same as 2004 MM4. The new orbit that they computed, linking the December and the June observation, revealed a very close approach to the Earth in 2029 with a significant impact risk. And in fact, the impact risk kept increasing as new observations came in until it got up to something like a 3% chance of an Earth impact in 2029. First object to ever reach level 2 on the so-called Torino scale of impact hazard. Most of the other discoveries were all in Torino scale 0, meaning either too small or too unlikely to hit. Then on 2004, December 27th, the Spacewatch project dug through their archive of images and realized that they were, realizes they were pointed at the right place to see 2004 MN4 on 2004 March 5. So they went back and looked at those images, and there it was at an extremely low signal to noise ratio, but they managed to get a position out of it, and the observational arc suddenly jumped from 6 months long to 9 months long, and that was enough to eliminate the 2029 impact scenario for this object. But right around Christmas time, 2004, the near-Earth asteroid community was all abuzz over this object because it had a significant impact risk in 2029. And some people called it the Grinch that stole Christmas. Okay, so there's the ruling out of the impact in 2029. Okay, 2005. Dynamicists discover a phenomenon that becomes known as keyholes. I'll say a bit more about keyholes on a subsequent slide here. So even though we had ruled out an impact in 2029, they discovered that impacts in 2035, 2036, 2037, 2038 were all still possible. So this object became much more interesting. Okay, so here's a diagram of the 2029 close approach to the Earth. The first item of interest is that, at this scale, the orbit of the asteroid would be virtually a straight line. And you can see that the gravity of the Earth is going to deflect it considerably in 2029. It's going to change the same major axis of the orbit from something that is currently less than 1 astronomical unit to something that is greater than 1 astronomical unit. So it's going to steal a little bit of orbital energy from the Earth and increase the size of its own orbit. And correspondingly, it's going to decrease the size of the Earth's orbit. So we're going to get a little bit closer to the sun, and global warming. Contribute to global warming. Well, no, you can do the math. It's like going to move the Earth by maybe a meter or less than a meter. But the I don't know, can you see the mouse here? This little white bar next to the Earth, that represents sort of the range of uncertainties at the time this diagram was made. The range of uncertainty in the miss distance. We knew it wasn't going to hit the Earth, but it might get as close as this point, or it might get as far as this point. So if you look at an orbit that brings it this close, it would orbit the sun a few times, the Earth would orbit the sun a few times, and then it would come back and miss the Earth to one side, say in 2035. But if you adopt the orbit that has it passing this far away from the Earth, the asteroid would orbit the sun a few times, the Earth would orbit the sun a few times, it would come back in 2035 and it would miss to the other side of the Earth. So if it's going to miss the Earth to one side down, if it's down here, and if it misses to the other side of the Earth when it's up here, that means that somewhere between these two extremes, there is a point or several points, a range of points that would coincide with an Earth impact. And that is what's called the keyhole. If the asteroid passes through the keyhole, it would come back and hit the Earth. So it was this discovery that led to this whole new field of study called keyhole science. Now, if it doesn't hit the keyhole, it could still pass close to the keyhole, which means that several years later, it would pass close to the Earth again. And we would have yet another keyhole situation. So a keyhole can have daughter keyholes, and those daughter keyholes can have granddaughter keyholes, and you can see how this very quickly becomes like a fractal diagram. So keyhole science has become a very interesting topic when dealing with near-Earth asteroid impacts. How big are these keyholes? Well, they vary in size, but something on the order of the size of the asteroid itself is not uncommon. So these keyholes are pretty tiny. Okay. I thought I'd spend a little bit of time here talking about the name Apothis. This is something that has been frequently asked about, how to get its name. And there's some misinformation that's out there in the cyber world. So by 2005, the official IAU designation was 2004 MN4, meaning it had been discovered in 2004. M is assigned to any object discovered in the first half of June. They use the letters of the alphabet by half months, except for the letters I, and Z is not needed because there are 24 half months and there are 26 letters. So you'll never see a 2004 Z something, for example, and you'll never see a 2004 I something. But A and the rest of the letters. And then the second letter is just assigned sequentially. Again, they skip the letter I, so you'll never see that. But MA through MZ, and if you run out of designations, they'll come back and do MA1, MB1, all the way up to MZ1, and then they'll loop back MA2. And so they loop through the alphabet 3 times. We were on the 4th pass through the alphabet in the first half of June with all the asteroid discoveries. So that's how it got the IAU designation. But people started referring to it by the nickname Minnesota 4. Minnesota coming from the postal code MN for the state of Minnesota. So people were calling it Minnesota 4, and we didn't particularly like that. We wanted to nip that in the bud before it became too entrenched. But the International Astronomical Union has some rules regarding the naming of asteroids. And one of the rules they adopted was that you couldn't name it until it had received a catalog number. This was to prevent the Hermes situation. This was a near-Earth asteroid that was discovered, oh gosh, early in the 1900s. And it got the name Hermes and then became lost. And so we had a situation where we had a named asteroid and nobody knew where it was. And the IAU didn't want to repeat that. And so one of the rules that they established was you can't give it a name until the orbit has been firmly established. And that is usually indicated by the assignment of a catalog number. And they usually don't do that until you have at least 3 separate oppositions of observations. It's usually 4 for a main belt object, but for near-Earth objects, they move somewhat faster. They have often relaxed it for near-Earth objects to 3 oppositions. So in 2005, we had 1 opposition of observations, or maybe you could count it as 2, I suppose. It did go through a solar elongation minimum between June and December, but still it didn't qualify for numbering at that particular time. At least until Sedna came along. Now, if you're familiar with Sedna, this is one of those objects way out beyond Pluto that was discovered by Mike Brown at Caltech, and he kept calling it Sedna. And a lot of people started objecting, saying, hey, you can't do that. You can't give an asteroid a name until it's got a catalog number. And objects out beyond Pluto orbit the sun so slowly, you know, it would take quite a while to establish the orbit well enough to give it a name. And but he kept calling it Sedna, and so they wound up adopting something that I call the Sedna rule. So there's a loophole. If an object is of extreme interest and not in danger of becoming lost, the IAU would allow you to propose a name for the asteroid in advance of receiving a catalog number. So we sat down, you know, Roy and Fabrizio and I, we all got together and discussed what we wanted to name it. And we figured we would invoke the Sedna rule to accomplish this. But the question was, what should we propose for the name? Now, there is a convention. Near-Earth asteroids of the Apollo variety, meaning they have same major axes greater than 1 AU, are by convention given the names of Greek gods. If you have a same major axis less than 1 AU, those are near-Earth asteroids of the so-called Aten variety, and they are traditionally given the names of Egyptian gods, an example being 2340 Hathor. Our discovery is currently of the Aten variety, but after the 2029 close approach, it will become of the Apollo variety, which raised an interesting question. Do we give it a Greek god name or do we give it an Egyptian god name? So we had to seek out advice from the Minor Planet Center, and they said, you have to go with the discovery circumstances. So they said, go with an Egyptian god name. Okay, there's just some samples out there of Aten asteroid names named after Egyptian gods, with a bit of an exception there. 2100 Rosh Shalom, that was named about the time of the Arab-Israeli peace accord. And so they thought they would kind of honor that peace deal by designating an asteroid, giving it the name Rosh Shalom. So that's kind of one exception among the Aten asteroids. And then there's some Apollo asteroids down there. You can see Daedalus and Cerberus, Sisyphus, Midas, Adonis, familiar Greek god names. Okay, there's a picture of Apothis. Not the asteroid, but the character from Stargate SG-1. That's played by Peter Williams in full costume there. Interesting. Kritari tells Shah, I mean, people of America, yes, we can. Which one's Peter Williams? Okay. There's a real picture of the asteroid. Well, maybe I shouldn't say a picture. It is a computer simulation of a shape model that reproduces the rotational light curve as observed from Earth. Pretty good sized object, about 300 meters. Well, the long dimension, probably a little bit more, maybe closer to 340 meters in size. It's a bit elongated. As it rotates, the brightness varies by almost a magnitude. So it's varies in about 30 hours. It's actually in a state of non-principal axis rotation. It is tumbling basically, or spinning about two different axes, one with a short period, one with a longer period. But the shorter period is 30 hours. And so it changes its brightness by almost a magnitude over 30 hours, which raises an interesting question. We can't extrapolate the rotational light curve to 2029 very accurately. So I can't say definitively how bright it's going to get during that April 13th close approach in 2029. It might be as faint as, magnitude 3.5 if it's unlucky and we pick it up at minimum light. Or we might get lucky and have it around maximum light, in which case it might get up to around 2.5 magnitude. So just some notes for those of you that are planning to observe the 2029 close approach. By the way, the best observability will be in Western Europe or the Eastern Atlantic Ocean or Northwestern Africa. Canary Islands would be a good place to see it at its brightest. It will be visible inbound. It will disappear into the daytime sky hours after the close approach. So don't wait for it after April 13th. Look for it before April 13th. If you're in the US, it'll still be naked eye, but it won't be third magnitude. Okay, back to the naming thing. So I have to say, Greek and Egyptian mythology is not exactly one of my strong suits, but I did know the names of a few Egyptian gods, primarily via exposure to the Stargate SG-1 television series. So those people who claim that the asteroid was named after the character from Stargate SG-1, that's not correct. It was not named after the character. The rules about naming them after Egyptian gods were already in place long before there even was a Stargate SG-1. But my familiarity with the names of Egyptian gods was enhanced via the viewing of that particular television show. But I still went onto the web to look up the names of other Egyptian gods. And what I discovered is that Apothis is actually the Greek name for the Egyptian god Apep, the god of evil and destruction. And I'm going, oh, this is perfect. We have an Aten class asteroid that's going to become an Apollo class asteroid. So we can give it a kind of a combination Greek name of an Egyptian god. And this asteroid was definitely evil. It was the Grinch that stole Christmas in 2004, and it's potentially very destructive if it were to hit. So we thought that this was a perfect name, but we did due diligence. We considered other names, but we basically came back to Apophis as being the best fit, the most appropriate name for this object. So we agreed to propose name. And we invoked the Sedna rule. We sent off our name suggestion to the Minor Planet Center. And the IU Names Committee approved the name, and they published the name in the citation in July 2005. But they also decided to go ahead and give it a catalog number at the same time. So basically, they're saying we didn't really need to invoke the Sedna rule because it had a catalog number. It's just that at the time the name was submitted, it did not have the catalog number. So I don't know, maybe the name proposal is kind of forced their hand and caused them to give it a catalog number a little ahead of schedule, because it was really a two opposition object at that time. So it didn't really satisfy their normal rules, but the orbit had been very well established by then anyway, because it was such an impact threat. People were observing it like crazy. So the orbit was very well established. Okay, so I'm dating myself here, but those of you who are old enough to remember radio news guy Paul Harvey, and now you know the rest of the story. Good day. But before I sign off, Apophis was in the news a few months ago. We gave a presentation at the 2020 DPS virtual meeting, and we announced that we had detected Yarkovsky acceleration on Apophis. And if you're unfamiliar with the Yarkovsky effect, well, when an asteroid absorbs sunlight, it has to re-emit that energy in order to maintain thermal equilibrium. If it didn't, it would just keep getting hotter and hotter and hotter until it eventually melted, and eventually it evaporate if it just kept getting hotter and hotter. So it's got to re-emit the energy that it gets from the sun in order to maintain thermal equilibrium, or at least approximate thermal equilibrium. Obviously, anything that's in an elliptical orbit, it's going to warm up as it approaches the sun, and it's going to cool off as it recedes from the sun. And there's going to be some kind of a thermal lag effect. So it may not be an instantaneous thermal equilibrium, but long-term average, it's got to maintain thermal equilibrium. Otherwise, it's going to melt and evaporate. So when an object rotates, however, the heat that emits is not going to be in the opposite direction from which it received it from the sun. So think about it for a moment. What's the hottest part of the day on Earth? Is it noon when the sun crosses the meridian? No, it's maybe 3 o'clock in the afternoon. What's the hottest time of year? Is it June 21st when the sun's highest in the sky for the Northern Hemisphere? No, it's probably August. So there's a thermal lag effect involved. It just takes materials longer to heat up and longer to cool down. So a rotating asteroid is going to emit the heat from a hemisphere that is not pointed back at the sun. So there is a net acceleration caused by the non-isotropic emission of thermal radiation. That's basically the Yarkovsky effect. And depending upon whether the object is rotating prograde or retrograde, it may cause the object to spiral inward or spiral outward in its orbit around the sun. Now, this particular figure I'm showing right now is from a 2015 paper by David Volkrulicki, and he shows on the right-hand side here these two gray vertical bars. That's actually a curve, but the peak of the curve is so far off the top of the diagram that you don't see it. That is basically where the asteroid would be under the influence of gravity only. And you can see some of the keyholes are shown here. The 2068 keyhole is toward the right. The 2089 keyhole is toward the middle. The 2036 keyhole is far to the left. And as you can see, if you used gravity only to propagate the orbit of this object forward in time, it would miss all of those keyholes, the ones that are labeled there. There's a couple of keyholes to the right, but it would miss those too, but pretty closely. And so you would say that this object is not an impact threat. However, once you take the Yarkovsky effect into account, the situation changes. Now, we already know from observations of the rotational light curve that the object is rotating in about 30 hours, and they have determined a pole orientation, and they believe it is rotating in a retrograde fashion. So this object should be spiraling inward. And this black curve basically shows the range of possible distances that it might pass depending upon the predicted values for the Yarkovsky effect based on what they know of the pole orientation, the rotation speed, and the thermal inertia, the range of possible thermal inertias for surface materials on Apothis. So this is the range of possibilities here shown by this black curve. And as you can see, the 2068 keyhole is allowed. It's within the range. So that's the theoretical prediction. We've been trying to detect it observationally for some time. This same paper in 2015, they took all of the available observations and tried to fit an orbit to the observations with a free term to represent the Yarkovsky effect, the so-called transverse acceleration, or A2 is the typical notation for that. They could not find a statistically significant value as of 2015. From 2015 to 2018, the object was in conjunction with the sun, so it was not possible to obtain more observations. In 2018 May, it was about 30 degrees from the sun, and we attempted an observation from our 2-meter telescope, and we detected it, and but it was extremely low in the sky. And by that time, we were using the new Gaia star catalog, and the Gaia star catalog is so good that it revealed the effects of atmospheric refraction on our astrometry. In other words, Apophis it's a little redder than the sun, and the sun, of course, is like a G2 star. But most of the stars within the field of view that we were basing our astrometric solution on were even redder than Apophis. So Apophis was a little bluer than the typical reference star. And as a result, it suffered more refraction than the stars did. And the displacement was something on the order of 1/10 of an arc second. So we kind of had to pause at that point and question, are we seeing the effects of differential refraction in the data, or are we seeing the effects of Yarkovsky acceleration? Big uncertainty there. Very small systematic effects in the data can mimic a physical effect, such as Yarkovsky, when in fact you might be seeing the effects of refraction. So we kind of hit the pause button at that point. And then in 2019, we got some more observations. But what happened in 2020, we had some time on Subaru. It was, Apothis was high in the sky during evening twilight. It was 19th magnitude. So all we needed was a 10-second exposure, and we got signal to noise ratio over 100. And we're using a filter, a red filter, so that kind of minimized refraction effects. Some of the other data have been taken unfiltered, which is why the refraction effects are so much bigger for them. And with Subaru, we were able to get astrometric precision better than 10 milliarc seconds, which just kind of blew me away. I'd never seen ground-based astrometry so good. And 3 consecutive nights, we got 5 exposures on each of those nights. So we got 15 observations that are all better than 10 milliarc seconds. And then in March, we had another night where we got 3 more exposures. And we made the presentation at the 2020 Division for Planetary Sciences meeting and announced that we had detected Yarkovsky acceleration. And it turned out that the detected value is very, very close to the predicted value. So pretty close to the peak of this curve that you see here. So we announced that the 2068 impact scenario was still in play. And we're in the process of writing up a paper now. In fact, we just finished the impact analysis. We ran 10 million variant orbits to take into account the uncertainties in the various orbital elements. We ran them for a century into the future, and we found 13 impacting scenarios, 8 of which are in 2068, and there are single events in 5 other years between 2068 and 2121. So basically the impact probability for 2068, we can now revise to as about a part in a million. So it's a very low impact probability. And I'm sure it will continue to get refined as we go forward in time. And of course, we'll know exactly what's going to happen after the 2029 close approach. Because right now, all of this uncertainty is being caused by the close approach in 2029, where all you have to do is change the position of the asteroid by a few meters, and the future position of the asteroid is going to change by kilometers, because the orbit's going to be just changed so much by the gravitational perturbation of the Earth. So that's just an update, because Apothis was in the news just a couple months ago, and that's our current status. The 2068 impact is still in play, but the probability is less than a million, 1 in a million. So with that, I will stop, say thank you all for tuning in, and I'm happy to answer as many questions as you got.
That was great, Dave. Thanks.
A very interesting presentation. What is the composition of the asteroid?
Okay, the spectral data obtained by Rick Benzel and colleagues indicates a taxonomic class that he calls SQ. So kind of intermediate between what we would call an S-type asteroid, of which there are plenty in the main belt, primarily in the inner part of the main belt. And the S is a mnemonic for silicates. So it's basically a stony type object. Now, the Q variety, I guess the type example for that class is the Apollo asteroid Apollo itself, 1862 Apollo, which has a somewhat stronger infrared absorption band, indicating the presence of perhaps a bit more pyroxene and or olivine. So, but it's basically a stony object. It is not believed to be of the iron variety, the kind that hit Arizona, Barringer crater, meteor crater near Winslow. That was an iron object. The Canyon Diablo meteorite. That's why that one made it to the ground and created a crater, a kilometer across. That one, even though it was only 50 meters in size, it was structurally intact and was able to survive atmospheric entry. So pretty much a stony composition. Can't really be too much more detailed than that because, we're limited to what we can get spectroscopically from our telescopes. Very broad absorption features in asteroid spectra. Oh, one thing I should probably add, you're familiar with the OSIRIS-REx spacecraft, which visited near-Earth asteroid and picked up some samples, and it's going to head back to Earth and drop off those samples. They are looking at extended mission scenarios. And there are 3 asteroids that they are currently looking at, one of which is Apothis. Now, unfortunately, it would not arrive at the asteroid until after the 2029 close approach, but it would be shortly after the 2029 close approach. So we may have a spacecraft going to this asteroid, and it may already be out there in flight.
Thank you.
That may be the topic, at least the mission of Umberto's talk in a month or two.
Oh, okay, that'd be great.
Or I'm assuming, I don't know, he hasn't chosen a topic, but since he's part of the mission, I would assume
Yes,
that.
yes.
Yeah.
You'd mentioned the Chelyabinsk meteorite